Let us recall the formula for Green's functions that we wrote, which was this. So if you have n external points x1 to xn, and you are looking at this correlation function, in the interacting field theory, we wrote down the master formula as the following. Okay, and then you had the exponential factor. This expression is in free theory, and then we have to divide this by the same thing as above except for the external fields, and this all is in interacting picture, and the phi i's evolve according to free field equations of motion. Sorry. I have forgotten a factor of minus I. Okay, lambda over, instead of h bar was 1, I should put a 4 factorial. Okay, so this is what we had, and then we wrote down diagrammatic expressions for these objects in perturbation theory. Look at the let's look at the kind of diagrams that you have in the denominator. Okay, so here there are no external points. There is no x1, x2, or xn. So here you have only internal vertices. So I will first write it as numerator. Divided by the denominator. Okay, by the numerator I mean what you have in here, and by denominator I mean what you have in here. Okay, so we have been writing Feynman diagrams for the numerator. Let's look at denominator. So denominator has this. If you expand the exponential, the first term would be 1, then you will have an order lambda term, okay, and then you will have order lambda square term and so forth, and at order lambda you will have the kind of diagrams that will appear will be the following. So let's say you draw this vertex with label z, internal point is called z, and then the only diagram that you can have is this one. If you are at order lambda square, then the kind of diagram that you can have are of these forms. So at order lambda square you get one diagram which is this. You also get a diagram which is, I'll just add them up, which will be this one, okay, and so forth. So these kind of diagrams which are not connected to any external point, these are called bubble diagrams. Diagrams not connected to any external point. Okay, so these such diagrams are called bubble diagrams. Okay, now let's look at the numerator again, and I want to this time look at 4-point functions, a 4-point Green's function. I'm looking at the numerator. So at order lambda 0, we'll have, so let me label x1, x2, x3, x4. So we'll have these kind of diagrams. Okay. Then at order lambda, you'll have this. So there is a vertex lambda here. Okay. Then this is at order. Maybe I'll write it in the next line. So this is lambdas. These are lambda 0 terms. And let me instead of write, let's write G4. Okay, so I'm writing the expansion of this. So at order lambda, you have lambda to the 0, these terms. Okay, and then at order lambda, you have terms like, for example, this term is there. You also have terms like, so this does not contribute any factor of lambda, but this one contributes. So here, for example, this is what is meant. Okay, and there are other diagrams. And then at order lambda square, you will have, among many other diagrams, the following. So this contributes order lambda, this also contributes order lambda. Okay, so these two vertices, they make it order lambda square. Okay, and you will also have these, and this is at higher orders. This is at order lambda cube. This one is order again lambda cube. Okay, 1, 2, 3. So you have many such diagrams. Okay, maybe one more I will draw to make it clear. So you can also have a diagram of this sort and a diagram of this sort. Okay, you can count how many factors of lambda you have to multiply. So you have all such kinds of diagrams appearing at different orders. Okay. Now I want to look at one particular diagram, which is this one. I choose it at random. There is no special reason for choosing this, but the point I want to make can be made through this or any other diagram. So I choose one. So let us look at the diagram. This. So these are the external points x1, x2, x3 and x4. Let me label the internal points as z1, z2, z3 and z4. So what's the expression of this diagram? It is, I write the Feynman propagator for each of these lines and include all the other factors. So I will do it. So the expression is the following. Let me give it a name. Let's call it f. F of x1, x2, x3, x4. Okay, so this diagram I have given a name, which is f, and this is equal to df x1 minus z1. So that takes this propagator, df of x2 minus z2, this propagator, and all the other ones, times df of, so this one z1 minus z2, and the second one also df of z1 minus z2, this one. Okay, and then I should write down all the, okay, not yet, I have these ones. So this is df of z3 minus z3, df of again z3 minus z3 for this one, and similarly the one for the other bubble. Okay. Okay. Now let's put all the factors of minus I lambda over 4 factorial. You have 1, 2, 3, 4. So you get minus I lambda over 4 factorial raised to the power 4. This is order lambda 4. So when you are expanding the exponential to fourth power, to the fourth order, that is what gives you lambda 4. It gives you minus I lambda over 4 factorial raised to the power 4 and 1 over 4 factorial, 1 over 4 factorial because of this. Okay, so this is the 4 factorial I am talking about. So you get 1 over 4 factorial times the combinatoric factors. Let me write it. So the factor, I will write on the next line. So let's count how many ways. So let's see, x1, x2, x3, x4. You have one vertex here, you have one vertex, another second vertex, third vertex, and fourth vertex. So you have 1, 2, 3, and 4. Okay. So let's count what is the factor here. So x1, this point is x1, x2, x3, x4. Okay. So I will urge you to do the calculation yourself first, and then try to match with what I have got and see whether you agree. So the first one, x1, could go to any of the 8 or some other number. It could go here, or it could go to this vertex, or it could go to that vertex, or it could go to this vertex. So you have 16 possibilities because there are 4 such with each having 4 little legs. So you have 16 possibilities. So x1 could go to any of the 16. So let's connect it to one of them, and whichever we connect, we call it z1. So if I had connected this one here, I would have called this one as z1, and it doesn't matter which one I'm calling z1, so I'll just connect here for ease. So you have 16 possibilities. Then this one has to go to the same vertex to which x1 is connected. It cannot go to here, right? Because that will give a diagram which does not look like this. So this one has only 3 possibilities, so it goes to one of them. Then x3 can go to any of these 3 vertices. So you have 12 options, right? So it can go to any of the 12 points. So let's say it goes to one of them, and whichever it connects to, I'll call it z2. So if I had connected this one here instead, I would have called this one as z2, and everything will still look the same. So this is z2. Now z4 has to go to the vertex to which x3 is connected. So z4 has only 3 options. So it goes there. It has 3 options. Now this one can connect only to this because z1 and z2 are connected. So this has only 2 possibilities. It goes either here or there. So it takes 2, and there's only one possibility here. Then here, this can only connect to itself. It cannot connect here because that will be very different looking diagram. So we have to connect this to itself, and there are only 3 possibilities. So it could go here, here, or here. So it goes to one of them. So there are 3 possibilities. Then there is only 1, and the same for this, which is again 3 times 1. Okay. I think I got every factor right, and if I made a mistake we will discover it. So anyway, this is what we get, and this is the full expression. Okay. Now you see that this is looking like this object of course has all these propagators which make up this one and this one. So if you see Z3 and Z4 up to here, okay, this one, and then so this one has propagators of exactly this one, right, and this piece has the one here below. The remaining these two lines have propagators only of these two. So we can think of this entire diagram as product of this piece times this piece. Okay, but not quite, because the factors may not work out correctly, and let me show you what I mean by that. Okay, so yeah, let me do that. So this I have done. Now I will look at a different kind of a problem. Okay, so let's look at f prime x1, x2, x3, x4, which is not the same as f. At least to begin with, it might turn out to be the same as f, but at this moment we don't have a reason to believe it's the same, which is this. So I am saying that this guy is this Feynman diagram. So I am defining f prime to be this. Okay, so f prime is defined to be a product of these two. So let's write down the expression of this one, and then we'll compare it with the expression of f. So here you get all the same propagators. Let me write it. It's boring to write, but I will write nevertheless. Okay, times. So this diagram is, see, the way I have written is you are given two diagrams and you are just multiplying them. Okay, this is different from the previous case where I was given one diagram. This is one Feynman diagram. Okay, and we wrote it this way. Now I am given two Feynman diagrams, so I should calculate this separately and calculate this separately. So for this one, what are the other factors? So this is order lambda square diagram. So it has a minus I lambda over 4 factorial raised to the power 2. This comes by expanding the exponential to second power. So you have 1 over 2 factorial. And let's write down the combinatoric factor for this. So point x1 has 8 places to go, 8. Then this one has 3 places to go, 3. And then this one has 4 places to go, 4. This one has 3 places to go. This one has 2 places to go, and finally 1. Okay, I didn't do it the way I used to, because I believe that I have done it earlier many times. So I am writing the expression. Okay, so this is this one times, let's write the expression for this. So df of z3 minus z3, df of z3 minus z3, then df of z4 minus z4, df z4 minus z4. Okay, so I've taken care of all the propagators. So you have 1, 2, 3, 4 propagators, and that's here. Now again, this is an order lambda square diagram because there are 2 vertices here and there. Okay, so it also gives you minus I lambda over 4 factorial squared. Again, because of the exponential expansion, you get 1 over 2 factorial. And then we have to count the combinatoric factor, which is simple. Again, this one can go to any of the 3. Okay, so it's 3. And then there is only one possibility. It's 3 times 1 into again the same. Okay, so this is what I meant by the product. Okay, so you see it's clearly this diagram, all its combinatoric factor and other factors times this one. And here you should think of this as one diagram, not product of 2 diagrams. Okay, so you see the difference, the factors in this and that are different. So let's compare the combinatoric factors, not just all the numerical factors rather than combinatoric factors. So let's compare let me write down here. So let us compare all the factors in f and f prime other than the propagators. Okay, because propagators are identical in both, there is no difference, right? Whatever you have in f, exactly the same ones appear in f prime also. So they are identical. The only possible difference is, the differences are only due to the other factors. So let's write them here. So let's write f prime and f. Okay, let's see. So I remember f prime has, from the bubbles, it had 3 times 1 times 3 times 1. Okay, and this also had 3 times 1 times 3 times 1, that was coming from the bubbles. And then there was this factor 6. Let me look at my notebook so that I can write easily. Okay, so this had 16 times 3 times 12 times 3 times 2 times 1. Okay, and then it had, sorry, which one I am writing, it's other way around. This was for f, so let me write here. This is wrong, I will erase it. Maybe I should first erase it. So it was 16 times 3 times 12 times 3 times 2, and f prime had this piece. F prime had 8 times 3 times 4 times 3 times 2 times 1. Okay, and then this is f prime. This I have taken care of. This I have taken care of. This one comes with a 1 over 2 factorial, and this one comes also with a 1 over 2 factorial. Okay, and they both also have minus I lambda over 4 factorial square. So I have, this was f prime. So you have minus I lambda over 4 factorial squared, then minus I lambda over 4 factorial squared, then you have 1 over 2 factorial times 1 over 2 factorial. And let's go back to f, the expression of f. You had minus I lambda over 4 factorial to the power 4 and 1 over 4 factorial. Okay, and let's compare these two now. So this line is, so these are all multiplied, of course. So this factor is same as this factor. the factors of minus I lambda over 4 factorial, they are identical. Okay. So let's look at this. This one. This one is 1 over 2 factorial times 1 over 2 factorials time this piece. So this 8 I can write as, sorry, this 16 I can write as 2 times 8. Okay. This 12 I can write as 4 times 3. Okay, and now let's compare. So this is same, the 4 is here, so I will look at this, and this 3 is there, and then this 8 is here. So what is the extra thing? The one which is extra is this 3 and this 2, so which is 6. Okay, so you have 6 over 4 factorial, and other factors are identical, and here you have 1 over 2 factorial times 1 over 2 factorial, okay, which is 1 over 4, and this is again 1 over 4. So you see that f prime is equal to f. Here I was looking at only the numeric factors. Okay, but once you multiply to these numeric factors the propagators, which are identical in both the cases, we realize that the f prime and f are identical expressions. Okay, which means that I have the following relation, that this Feynman diagram is same as product of this times this. Okay, even though they do not appear to be same, but we have seen explicitly that the combinatoric factors and other factors combine in such a way that all the factors are same on both the sides. Okay, so this is what we have proved, and let's see why this has come out to be true, and we will see that this is not something that has happened accidentally for this particular diagram, but rather it works for every diagram. Meaning, if you have a diagram which has some bubbles in it, then that diagram can be written as a product of diagram with the bubbles times the diagram, the part that appears in here without bubbles, that appears as a product here. Okay, so this is going to be true in general, and let's see why it has worked out this way. Okay. So let's look at any diagram of this variety where you have some piece which does not have any bubbles and may have any number of legs. Okay, so this one has no bubbles. Any number of legs it may have, and then there is this piece which has some bubbles. So this diagram could be, for example, this one. It could represent, let's say, this. Okay, whatever you prefer. This could be diagram, which is this. So as I said, this side is not two diagrams, not a product of two diagrams, it's one single diagram. So I'm still drawing this. So this could be something of this sort. Okay, for example, this diagram could denote this. And so the claim we want to make is that this can be written as this diagram standing on its own, times the same bubble diagram which you have here, okay, and the combinatoric factors will work out so that this equality holds. And now let me argue that this is indeed true. So here, suppose you have n vertices in this diagram, which means in this case you have 1, 2, 3, 4, 5. So in this, for this example, n will be 5. Okay, let's look at this one. It's 1, 2, 3, 4, 5. Okay, that's looking too much of, so we can have this and we can also have this. So let's say this is actually this diagram. Then 1, 2, 3, 4, 5, 6, 7. So this has 7 vertices. So I say that in general this will have some m number of vertices, and m is 7 in this example. Okay. Now when you are calculating the propagators in this, writing down the propagators, it will be identical on this case, so I don't worry about it. The difference was coming from these pieces, right? Because instead of having a 1 over 4 factorial in this f, you had a product of 1 over 2 factorials in f prime. Okay, so that will be the source, one source of difference. So let's first calculate the factors of these factorials coming from the expansion of the exponent. Okay, and I don't worry about minus I lambda over 4 factorial because they are identical in both. So this one, left hand side will have, so this diagram becomes of order n plus m, right? This will have n plus m vertices, so it's an order lambda n plus m diagram, and then you will have, maybe I will write this piece just to help reading the order, and then this comes with 1 over n plus m factorial. Okay, n plus m factorial times the combinatoric factor of this entire thing. So let's call it C left hand side, C for combinatoric and for the left hand side. Now right hand side will be a minus I lambda over 4 factorial power n, because there are n vertices in here, power m because m vertices here, so that makes n plus m again. Okay, or maybe I can write in 2 steps. And then this one will come with 1 over n factorial, this one will come with 1 over m factorial times the combinatoric factor on the right hand side. Okay, so now let's look at the combinatoric factors on the 2 sides and then compare. So here, when you are writing down the combinatoric factor for this diagram, you do the following. Let's go back to how we did that one. So here this piece, when we were writing here, the x1 had the possibility of going to any of these 4 vertices, right? I could have connected here or there or there or there, and that's why you got a factor of 16. The 16 was basically 4 times 4, okay, because it is, each one is 4 possibilities, but there are 4 vertices. Okay, so what I can do is I can think of it as this diagram going, this x1 going to, so I just count the combinatoric factor of this one, and then I allow for the possibility that it could have gone to different vertices, okay, different ones. So when x1 is going to connect to any of these 4, it had the following number of choices. I mean the vertices to which it could go to was the following. So you had to begin with total of 4 vertices, okay, and you have selected 2 of them. Okay, so now I'm looking at this piece actually, and this is made up of 2 vertices. So out of these 4 vertices, I have selected 2 of them. Okay, and that is this number. So you can in how many ways you can select out of 4 vertices, 2 vertices? It is this, which is okay. And then on the top of it, you just have to calculate the combinatoric factors of these ones and these ones separately, right? Because there is nothing else. Let me show you. So this is, what is this number? Okay, let's go here. It will be easier, I think, there. So you see, when I am drawing this diagram, the vertices I have, so you think of having certain vertices placed here, and then you draw this diagram, okay, but you could have chosen the vertices in this one also to draw, okay, and the total number of possibilities you have is the following. So you have total of so I'm writing CLHS. You have total of n plus m vertices, and out of which you have chosen to use n of them to make your one will come with whatever vertices are left, they make up the bubble, and it comes with whatever combinatoric factor it has. Okay, and I forgot to say that this also comes with whatever other combinatoric factors it has. Okay, so the combinatoric factor of this times the combinatoric factor of this one times the different choices that you had for choosing the vertices from the remaining ones. Okay, so these are the total number of these are the different combinatoric factors that you have. Okay, if it is not sounding very clear, which it could be, you fall back to this example that I gave, and then it is clear. Okay, and let's look at the what happened. It's frozen. Okay, it's not writing. Okay, let's look at the right hand side. Right hand side had just C corresponding to no bubbles times C bubbles. Okay, so because you just multiply this, the combinatoric factor you get from here, and then what you get from here. Okay, and then now I should see whether if I include these factors they match. So let's multiply with 1 over n plus m factorial on this one. Okay, now this is not just C, but it is numeric factor now. Maybe I should not disturb that. So numeric factor on the left hand side is 1 over n plus m factorial times, I am writing this expression, this is n plus m factorial. So this is basically NCR, and it is n factorial divided by r factorial times n minus r factorial. Okay, so that's what I am writing. So it's n plus m factorial over n factorial times n plus m minus n, which is m. Okay, somehow it's not. Okay, this piece times C with no bubbles times C with bubbles. And what is the numeric factor for right hand side? It is just 1 over n factorial times 1 over m factorial, because that is what we had here. Okay, and the CRHS is just C times C of no bubbles times C of bubbles. And you see here that this cancels, and this piece is exactly as this piece. So you see that all the numeric factors on the left hand side and the right hand side are same, and that is why in general f prime is equal to f. Okay, so that's what we have proved. Okay, good. So with this we can make a nice statement. You see that the numerator of our master formula is basically you can write it as sum over diagrams without bubbles times 1 plus diagrams, sum over diagrams with bubbles. Okay, let me tell you why I am saying that. So if you look at again the 4-point function, maybe we go here. We have drawn many diagrams already. Here. So you see any diagram, if you look at this one, now you can think of it as this times this. That's what we have shown, right? So each diagram is some diagrams times some a diagram without a bubble times a diagram with bubbles. Okay, and if you have a diagram here in the numerator which has no bubble, then you can think of it this as multiplying 1, and that is the one here. That's the one here. Okay, so you can write this, and diagram denominator is anyway sum of all diagrams with 1 plus, denominator is 1 plus sum over all bubble diagrams. Okay, so you see now that this 1 plus bubbles in the numerator and 1 plus bubbles in the denominator, they cancel because we have shown that the numeric factors are identical in both in these cases. So what you get is eventually this, that the Green's function, n-point Green's function can be written as only sum of diagrams without bubbles. Okay, so when you are drawing, when you are writing an expression of a 4-point function, let's say G4 at order lambda, let's say order lambda, then you have only this diagram. Okay, you don't have to include this one because this is also there, but this you can discard because this is a product of a diagram which is without bubble and with bubble. So this one you can discard, or this one also you can discard. All you have to keep is this one at order lambda, and if you are at order lambda square, let's see, you have to begin with you had this one, for example, but this you can discard because it's a product. You just have to write this lambda square, so this okay, so only these ones, and all the diagrams with bubbles will be dropped. Okay, so we have a good nice result that we do not have to worry about the bubbles at all, okay, because they cancel between the numerator and the denominator. Okay, good. So we'll stop here and we'll meet in the next video.